Hi everyone. Right, so what do we have here? Well, I have got an off-grid solar PV system, and it uses a 24 volt hybrid inverter, and it collects power from the solar panels and it puts this into a battery, obviously, and then from the battery it inverts it into 230 volt AC because we're in the UK. Now, I've got no monitoring system on this. This is a fairly budget inverter. This is a fairly budget hybrid inverter. There are monitoring systems you can put on it, but they're fairly clunky. And so I decided that I want to do a little project, which turned out to be a rather big project, actually, and I've learned quite a lot from this. So hopefully I can impart some of that learning onto you. So I wanted to use an Arduino. Well, I wanted to use something. I wanted to use something to measure the voltage of this battery bank, and I wanted to measure the power or the current that was going in and out of these batteries at any given time. And crucially, I wanted to be able to log this data. And I wanted to be able to log this data against some sort of timestamp. So I wanted to be able to have the time and date as well, which I'll show you how to do that after. And of course, I wanted to make sure that everything was protected and nothing was going to blow up. And so to do this, I decided to use an Arduino, which has taught me a heck of a lot in the last few months putting this together. So I worked out how we can measure the voltage using an Arduino of this 24 volt battery pack here. And I worked out how we can measure the current. And so I used a CT clamp to do that. I may as well show you a picture of the CT clamp actually while we're at it. This is the CT clamp, which goes around, your cable goes through that and measures the current. Now, from measuring the current, which is either going into the battery or going out of the battery, I can then record that data. Here we have date, time, voltage, current, power, which is current times voltage. I can use this data then to make a graph, which I drew up in MATLAB because there's so much data here. Excel just kind of crashed. And I can sort of like think about what I'm seeing. So anything above zero current obviously is the load. So any energy that's going out of the battery shows up as a positive. So this is load. And any energy going into the battery here, which can either be via solar or generator, shows up as negative. Okay, I know that I put the generator on here just to test it. So we went from a fairly dark day, but didn't have much solar, to us dipping down into like minus 15 amps, something like that, of current. So in the next few videos, or in the next long video, I'm not sure how I'm going to do this. I might split it up, or I might just keep it as one. I'm going to show you how I managed to achieve this. So how did I manage to achieve measuring 24 volt, measuring the voltage of a battery bank, 24 volt battery bank? How did I manage to measure the current going in, the current going out? How did I log this data? How did I produce this graph? Okay, I probably won't show you how I produced the graph, but I'll show you the rest of it. One extra thing I'd like to say before moving forward is, so far we've been looking at the voltage and current of this battery bank here, but we could quite easily move this CT clamp to wherever we want. So we can move it to the solar panels if we want, and then we get to measure the current coming from the solar panels. We could also take the voltage measurement cables, and then we can put them onto the solar panels as well, so we can measure that, and then we can log that data. So then we've got some data from our solar panel input. It's not either or. We can put a couple of sensors into this Arduino, so we don't have to just measure one thing at a time. We could put as many sensors as can fit into this board actually, and do it that way. So it's just to tell you that we're not limited to measuring just one circuit, and this is just an example. We could use this to measure the current on any circuit. So the first thing we've got to do, measuring voltage. Let's have a look at that. Well, the analog pins in our Arduino, so I'm going to assume that people already know how these Arduinos work roughly. So we have analog pins, and this is where we're going to measure our voltage. Now, if we connect a 24 volt battery bank up to the Arduino, it's just going to blow it. Arduino analog pins can only accept 0 to 5 volts maximum. So how do we do this? How do we go about measuring a 24 volt battery bank with an Arduino? Well, very, very, very common circuit which you'll find online is a voltage divider circuit. And the idea here is we put the input through 2 resistors, then we tap off this leg here in the middle, then this goes to our analog input here. Now the key here is selecting the right resistors. So what we want to do is take 24 volt and we want to scale it down so 24 volt here equals 5 volt here. And we do that simply by selecting the correct resistors. Now I don't like reinventing the wheel, and if something is good online or so there's a good video on YouTube about it, then I'll always try and direct you to it. One of the best websites I've seen for calculating for calculating the voltage divider circuit is this here, and we're going to go and visit that now. Let's have a look at this website then. So we've got our equation here. This is our voltage source, Vs, R1, R2, and our output voltage. Well, we know that our output source, or our source voltage, sorry, is our 24 volt battery bank. However, and we'll see this later, a 24 volt battery bank is not really 24 volts, okay? It can go up to like 28 volts when it's charging. And a full 12 volt battery is about at least 12.5, maybe 12.7 volts. So how is this working? Well, things that we know. We want our output voltage here to the Arduino to be 5 volts, all right? So we'll put down 5 volts for that. We want our source voltage to be, why don't we call it 30 volts? Then we safe them. And we need to choose a resistor value. And I'm just going to choose 33k kilo ohms because I've seen on other videos that this is quite a common resistance to use as R1. And also you can get a 33 kilo ohm resistor, no problem. So what does that give me then? The resistance of R2. So what this is telling me is if I have an input voltage source of 30 volts, and I use this voltage divider circuit, and I use resistor with a value of 33 kilo ohms for R1 and 6.6 kilo ohms for R2, which we just calculated here, then I'm going to get an output of 5 volts. So if I go to this circuit here, which is tinkercad.com, we can see this in action. All right. So here I've chosen my 33 kilo ohm resistor, and here I've chosen my 6.6 kilo ohm resistor. And this is a voltage generator, and this is simply a multimeter. So what am I doing here? I'm with this multimeter, I'm measuring the voltage between this terminal and this terminal, which should give me the voltage that's on the multimeter. And I'm also measuring the voltage between the ground pin of the Arduino and our A1 pin, which the output, the center tap of this voltage divider circuit is going into. So let's have a look what we've got. So let's ramp up the voltage. So as you can see, we've got 12 volts here, 12 volts here going in. But what have we got out? Oh, we've only got 2 volts. So if I increase the voltage all the way up, what you can see is the voltage on the voltage generator is going up, but it's being scaled down because of these resistors to the input of the Arduino. So at 30 volts in, how much should we get out? Well, we just measured this, we just calculated it should be 5. Let's have a look. At 30 volts, there we are, we have 5 volts going into the Arduino, which is the maximum amount allowed. Fantastic. Now we can use the code now to tell it that it's doing all of this, and we've got ourselves a nice voltage divider circuit there. Do you know what? I want to come back to this because I don't feel as if I was explicit enough about this doing the video, so I've come back to it. So this voltage generator here, this is meant to be representing our battery. So if we increase our voltage on the voltage generator to something like, I don't know, something like 24 volts, should we say? There are 24 volts. We're actually only drawing a very small amount of current there as well. So 24 volts, and our battery gets scaled down to about 4 volts. I'm going into our Arduino pins. Now I've gone up to 30 volts here, right, because this is the maximum that this will allow. Now at 30 volts, we have a 5 volt input to our Arduino. Now there's nothing stopping us from increasing this voltage further. However, it will blow up the Arduino. So we've got a hard limit here of 30. I shouldn't have done this. I should have done it a little bit less to show you. But of course, if we put any more than 30 volts into this, we will increase the voltage here as well, so thereby destroying the Arduino. So our maximum voltage that we can put into our circuit with these two resistors is 30 volts. Anything more will destroy the Arduino. Okay, I want to be more explicit about that. Right, so knowing what we know about the voltage divider circuit, we can now start putting this all together with the Arduino. Ignore all this for now, this is just the data logging portion of it. Just focus on this. This is our battery voltage measurement circuit. And I've said here, this circuit can measure up to 37 volts. Well, how can that be then? Let's have a look at what we've done. We've got two 12-volt batteries connected in series. We've taken the negative out, and we've connected it to ground in the Arduino. I've then taken one wire or cable out through a 0.3 amp fuse. We'll talk about that later. It's probably not going to do anything. Through our 33 kilo ohm resistor. Then we've got a 5.1 kilo ohm resistor. Why is that? We'll talk about that now. And then the center tap here is going out to A0 in this case. So why 5.1 kilo ohm? Well, you know, you can't necessarily, this is real life now. You think you want a 6.6k resistor, but you look in your bag of resistors, you simply can't find one. But I found a 5.1k. What does that actually mean? It doesn't really matter in this case, because if I use a 5.1 kilo ohm resistor, I can actually measure up to 37 volts now. Okay, it's changed the circuit. You can go back and you can do that sum for yourself if you want. You'll find it. You'll find the number 37 comes out. Right, what we're going to talk about next, let's talk about the power supply. So the Arduino needs a power supply. If you're doing work on the desk, you know, with your computer handy, you can just plug it into the USB and everything's fine. However, remember, this is for an off-grid system. There's literally no power. Well, there is power, but where is our source of power? Well, it's these 12-volt batteries here. So we're off-grid, use the power source we have, which is our 12-volt. And that's what we're going to be talking about next. So we've got a 12-volt, 24-volt battery supply. Bearing in mind that the supply to the Arduino, some say it can take 20 volts max, but realistically, we're talking about a supply voltage between 9 and 12 volt, which that's recommended. And which will probably draw a current of 0.5 amps to 2 amps. I think 2 amps is probably a bit big, but it might do. So our power supply has got to at least be able to cope with this. How are we going to do this then? Right, we need to get 24 volts down to 12 volts, so we're going to need some sort of voltage regulator. The two voltage regulators that I have to hand is this LM2596 DC-DC buck converter, which is adjustable, which means I think you can put, whatever it is there, you can put up from 3 to 40 volts in, and you can regulate it between 1.5 and 35 volts. It's adjustable. And we've got a current rating of 2 amps, which is good, because that will be sufficient. We've also got here an efficient car power supply transformer. Well, it's hardly a transformer, but it's a voltage regulator, which takes us from 24 volts down to 12 volts reliably, and it's fuse protected as well. Much bigger unit, much more expensive. I think these are about £2 each. This cost me about £10, I think. So as I was saying before, we have a 12-volt battery, which, if we look at this here, this is the state of charge versus our actual battery voltage. So at 100% state of charge, our battery is, you know, it's behaving, it's sort of floating around 12.73, something like that, volts. Our 24-volt battery bank is about 25.46 according to this. When the battery's actually charging, and I've seen it myself, we can get up beyond 28 volts. So what can we do then to power up this Arduino? Well, we need 12 volts, so we could tap off 12 volts from our battery. But what we found is that what we've seen here is that a full battery is not 12 volts, it's 12.7 volts at least, or even more, 14.5 volts when charging. So we're going to need some sort of regulation, so we could use a buck converter here to give us between 9 and 12 volts out, or I should say really 9 to 11 volts out, possibly. The reason why I say that is because we have some some concerns with this. When I do try and regulate from about 12.5 volts down to 12 volts, it doesn't really work. I don't think there's some parasitic voltage drop that's going on inside this buck converter, which doesn't allow it. But it's fine, we can use it. Theoretically, if we do this, we should really never damage the Arduino, because it can only output 14 volts and at the maximum, so it should be okay. Like I said, cons here, we might not be able to regulate from 12.7 down to 12 volts, and I'm actually going to do another video on that to prove that. Well, not to prove it, just to show you what I did, basically. So, what's the other way of doing it? And this is the way I prefer to do it, is we could actually use the 24 volt system. So we got voltages between about 25 to 28 volts in. We can use the buck converter again, or the voltage regulator, to get us down to 12 volts there, okay? Notice how this power circuit is completely separate to this voltage divider circuit, alright? Pros here, well, our voltage regulator is actually designed to be able to do this. It gives us 12 volt out with ease. The buck converter will probably be able to do this as well, and the buck converter is very cheap. I guess I put here as a con, there's a possible chance of somehow sending 28 volts into the Arduino under component failure, but I don't think that's going to happen, because if the component fails, it'll probably just input 0 volts. I have had buck converters fail on me in the past, which is not ideal. So there we are, that's how we're going to power up the Arduino. Right, let's talk about current now. So we have our voltage divider circuit measuring voltage, and that's going into A0, and that's what we will use on the code to tell it what pin is doing what. Now we have to measure current. Well, our current should be measured from the load, which is here. So this sits here. Our load is our inverter in this case, alright? So we want to measure the current going in and out of this. When you buy one of these CT clamps, the instructions might tell you that they come with a red. By the way, this is a HST SO16L or LF. I can't really work out the difference between them all. But they say they come with a red, black and a yellow wire and a white wire. They don't. I can assure you that they come with a green cable and a red cable and a black cable, and the green cable is our V out. Okay, so that's our signal cable, and that's going to be connected to an Arduino analog pin. And then we've got the red cable, which is connected to our 5 volt, which comes from our regulated 12 volts here. And then we've got ground, then simply connected to ground. So that's our CT clamp. This is where you can get a data sheet for it, and we will work out some stuff from that data sheet for the code. So we're going to be doing that next. And here's a video of that, the CT clamp. So we got red, which is 5 volts, black 0 volts, and green here, which is V out. And then we got the shield then on the cable, which you don't do anything with. What else have we got on this? Well, we got the name of it, which is YH. I think it's YHDC, is it? HST 016L/F is 50 amp, and the numbers we're interested in here are 2.5 plus or minus 0.625 volt, which will become important in a minute. If you open it up, you can see there's an arrow, and the arrow will tell us which way the current's flowing to give us a positive current. So if the current's flowing in this direction, we're going to have positive values, and if the current's flowing in this direction, we'll have negative values. And I'll explain how that happens in the next video, or next slide rather. So what do we have to do to get this to work? Well, obviously when the current goes through this CT clamp, that's all it's going to do is change the voltage. Okay, so it's going to change the voltage, being red in A1 in this case, the green cable. Right. So how is it going to change the voltage? Well, let's have a look. So these CT clamps, when you power them up, they give out 2.5 volts. And at 2.5 volts, that is saying that we have 0 amps. So what we want to work out is, if we have 1 amp flowing through this circuit, what will our voltage be? Now, we have all of the data given in the datasheet, even though it can be quite confusing, so that's why I'm going to go through it here. We have the 4 direction, which gives you this formula, 2.5, which is here the center voltage, plus I, which is our current that we're measuring, over IPN, which is our rated current, input current, multiplied by 0.625, which is here. Right? So for 1 amp, 1 amp divided by 50 amps, amps and amps cancel, we got 0.02, that's a raw number. Then we take that number here, which we've just calculated, multiply it by 0.625 volts, which gives us 0.125 volts or 12.5 millivolts, a number which we will use in the code. So the question is, what's our voltage when we have a current of 1 amp? Well, in this case, we just add 2.5 to the number we've just calculated here, which gives us 2.5125 volts. So in this case, question mark equals that. So here we go. So 1 amp, we've got this voltage that we've just worked out. So another way of saying this is that we have 12.5 millivolts per amp. So every amp that we register, we increase the voltage by 12.5 millivolt. All right. So what about 50 amps? Well, at 50 amps, we've got 50 over 50 is 1 times that, 2.5, 1 times that equals that, obviously, 0.625. So 2.5 plus 0.625. This is, now we're starting to understand now where our 0.625 comes from, our plus or minus 0.625, because at the maximum of 50 amps, we have positive 0.625 volts. So we should read 3.125 volts at 50 amps. All right. And of course, all of this happens in reverse as well. So we've got 50 amps here, minus 50 amps. And that's why we use 2.5 as a floating voltage in the middle. So that's how we work out our current. And this will all become much more apparent when we have a look in the code. Because all of these numbers... Sorry, I won't say all of these numbers. I'll say this number here is the one that we use in our code later on. We've had a look at voltage. We've had a look at how we regulate the voltage coming in. We've as a power source rather. We've looked at how we can use a voltage divider circuit for the Arduino here. Okay. And we've looked at how we can use our CT clamp to provide a signal here at A1. These all might change, by the way, in reality, but this is what we've got written down here. Let's have a look at data logging them. Well, if you get an SD card reader, which looks like this, SD card reader writer, like this one here. We've got pins on it, ground, VCC, MISO, MOIS, SCK, and CS. Well, if you go and have a look on how to actually wire this up to the Arduino, here it is. We've got ground and VCC, which are connected. Ground's connected to ground, obviously. We've got VCC, which is connected to 5 volts. MISO is connected to pin 12. MOSI is connected to pin 10. SCK is connected to 13. And CS is connected to pin 10. Alright? Which we can define in the code. This pin 10 here. Our real-time clock, what the real-time clock does is basically you set the time of it. It's got a little battery in it. And you set the time. And here's a real-time clock here. There's a battery on the other side. And it holds that time. And then it provides you time and date data. So it's got ground, VCC, SDA, and SCL. They're the only ones we're interested in. And they get connected. So SCL gets connected to an analog pin. SDA gets connected to an analog pin. Now, that's all I'll say about that, because I'm not actually going to be using this I'm not actually going to be using these two here. I'm going to be using this, which is an SD card shield. I got this off eBay. It's made by Deek-robot, and it's a data logging shield version 1.0. And so all of this can be replaced simply by the data logging shield. And that's all you've got to do is define which pin comes out of it, which is pin 10 in this case I've used. And I think you have to use pin 10. And if you have a look at the Adafruit manual for this, and maybe I'll go into this in more detail, it talks about why, and on this video in a separate one, it talks about why we can do away with all of these cables here, these wires rather, and we end up with a very neat solution to logging data rather. And we'll have a look at a video of putting this together. So there's my Arduino Uno, and there's my data logging shield. So they simply just slot together, the pins, the female pins in one, except the male pins in the other. And then crucially, we've also got female pins at the top as well, which I can put an extra circuit board in, which I'm going to do. So here we have the real-time clock, which has got the battery. Here's your SD card, normal SD card. And crucially, there's a reset button on this, which is going to become really handy in this project. So important code variables. These are, if I just pull up the code, just a little bit of the code here, pull it into screen. This is our code, right? And we'll go through this in much more detail. But things are important. Line 19, A1, okay? This defines A1, which is our volta divider output rather. Line 25, we define our voltage supply value. Line 26, line 27 are our resistor values. Line 33 is our CT clamp Vout, our green cable. Line 34 is our millivolts per amp, which is 12.5 in this case for a 50 amp module. Line 52 is a current offset, and line 90 sets the communication pin for the SD card shield. I've already said it's pin 10. And line 94 sets the time interval between logging data on the SD card. And line 126, this sets the time and date on our real-time clock. In this final part of the video, I want to look at protection. And what are we trying to do on this? Well, let's have a look. Protection. Well, we need to put some fuses in the circuit. And why? Because we need to protect the cables. This is 12 volt we're dealing with here, not 240 volt. We're not really going to kill ourselves, but we could set things on fire if we have short circuits. So we need to protect these cables. So we've got a couple of cables coming off the 12 volt terminal here. We've got one going into the input, the barrel jack of the Arduino, and according to the internet search, the extensive internet search I've done, which has not been that successful, I found that this input here can take up to 2 amps, but it regularly takes about 3 to 500 milliamps. Also, this buck converter here, which I'm going to use in the circuit, in one of the circuits anyway, that can have an output of 2 amps maximum. So at least it satisfies the draw of current if we need 2 amps. We're probably not going to go anywhere near 2 amps. But anyway, I am going to be using a 0.75 millimeter squared cable, which, depending on what type you buy, the 3-core can take 6 amps. If you buy single automotive style, it takes about 14 amps. So if I put a 1 or 2 amp fuse here, it should be absolutely fine. It'll protect this cable. Remember, fuses aren't there really to protect the device itself. They're just there to protect the cable. Can I actually, maybe in this case, coincidentally, or whatever the word is, manage to protect both at once? I don't know. We'll see. So we've got fuses to protect cables, not equipment. My cable can handle 6 to 14 amps. So even if I used a 6 amp fuse, I shouldn't have any issues with this at all. The cable will be protected in the event of a short circuit. Buck converter can handle 2 amps. My Arduino apparently can handle 2 amps as well on the barrel jack. The Arduino is really only going to draw a very small amount of current, less than 1 amp. I've actually had a 500 milliamp fuse in here for weeks and it hasn't blown or done anything. So I'm going to say in this example, I could get away with a 6 amp fuse, and that would protect the cable, but I'm just going to try and see if I can limit it to a 500 milliamp fuse, sorry, not 500 amps. And this might have some protection for the equipment, but it does mean it derates it. So obviously this equipment now can't draw over 500 milliamp, or not much more over it anyway. In my case, this is fine because I'm not drawing much current anyway. So I'm going to stick a 500 milliamp fuse in there. Alright, I think I'm going to go forward with that. What about the voltage divider? Well, let's familiarise ourselves with measuring our voltage here. We've got our voltage divider circuit. We're not going to go through it again. But let's convert this now into a more standard type of circuit, which is easier to analyse. We've got the Arduino here. So everything else we've seen all this. We've got our V in. I'm going to try and size a fuse here. I'm telling you that the wires I'm going to use are 0.75 millimeters squared, I think that's what I've got. If it isn't, I'll just readjust. And in this case, I've done it quite accurately. If I have a V in of 30 volts and I use these resistors here and get a V out of 4 volts here, what's happening to the Arduino? Well, the Arduino has got an input impedance, so you can think of that as a resistor from A0, or the analog pin, to ground. And it's got a very, very high resistance. I mean, the calculations I've done here are for 1 mega ohm, but from what I've read on the internet, the input impedance of an Arduino is actually 100 mega ohm. But what does this mean? Well, if we get a short circuit, obviously between positive and negative, then we are definitely going to be drawing the full brunt of the battery here. And if we put a 6 amp fuse in here, then it's going to blow, and our wires are going to be protected. All right, if we get a short circuit in this region here, so from here to here, which is possible. But what I want to do is have a look at short circuits on other parts of the circuit. So say we have a short circuit across the 5.1 kilo ohm resistor, so that's here on the V out. Well, so just simply Ohm's law. Okay, how much current is going to flow? So obviously the current is going to flow through this 33k resistor down to ground. And how much is going to flow? Well, I equals 30 volts divided by our resistor, which is 33 times 10 to the 3 ohms. So we've got 0.91 milliamp flowing. In this scenario, our 6 amp fuse is going to do absolutely nothing. It's not going to blow. Our Arduino input is actually connected to ground and is fairly safe. Nothing's going to happen here. So if we get a short circuit here across R2, then we're safe. So we don't really need to worry about that part. Let's look at another scenario. Well, in a different scenario, let's say we have an open circuit here, which again is, I guess, is possible with a dry contact or something like that. So you need to be careful when you're soldering. And also if the resistor fails in some way, you might have an open circuit. Well, this becomes now actually another voltage divider circuit, with our R2 being our input impedance resistor here. So now we can say, well, what if we do have an open circuit, what's the voltage going to be across here? Well, we can work it out, and we can work it out from this equation here, which we've worked out already. And if we put the numbers in, and we got 30, which is Vs, times by R2, which is now I've called it 1 mega ohm, divided by R1, 33 kilo ohm, plus 1 mega ohm. What do we get? We get 29 volts. And you can do this online. Do this on the online calculator. In fact, I'll do it. So here we've got our voltage divider calculator. We've seen this before. So we've got a voltage source of 30, our R1 of 33, our R2 is now the input impedance of the Arduino. And we're going to say, well, okay, I've jumped the gun here a bit. Let's call it 1 mega ohm, like we've said. Call it 1 mega ohm. Then our output voltage is 29 volts, as we already calculated. Our actual input impedance of the Arduino is about 100 mega ohms. So what does that equal? That's 29.99. So it's basically Vs, isn't it? We've got such a massive resistor on R2 that our V out is basically the same as our Vs, isn't it? There we are. Right, so we worked out the voltage across this resistor here, which is over 5 volt, so we should know if we get an open circuit here, we're in trouble. We're gonna damage the Arduino, so we need to be careful of soldering the resistor in, and we can't really do anything about a faulty resistor, so I guess we can check it before we put it in. What's the current going to be like across here? Well, how much current is flowing here, where we've got two resistors in series. We've got our voltage of 30, so 30 divided by our two resistors in series gives us 0.03 milliamps. So we've got very, very little current flowing through this A0 here if we have an open circuit. We do have a high voltage. So trying to protect this equipment with a fuse is pretty much a no-go, and so we can't do that. But we can protect our cable, and we can protect it with a very, very small fuse if we like, less than 6 amps. What people normally do in this situation is they use a Zener diode in parallel with R2, and I'm not going to go through why people do that, but it works. And you can look on YouTube and you'll find loads of videos about protecting your Arduino using a Zener diode across R2. And that is it for the protection part of this video, I think. Anyway, that's my final circuit. Hopefully that made sense to everybody. Who knows, I might split this up into smaller videos, but I don't think it was that long, was it? Anyway, you let me know in the comments. If there's anything else you want to know, just let me know in the comments. I'm sure you will. I'm sure there'll be nice comments. I'm sure there won't be. That's just the way YouTube seems to work, isn't it? Okay, in the next video, I'll be showing you this circuit. I'll be putting it together live on the desk and showing you how it all works. Cheers. Hope you enjoyed that. Bye.